All right, so your test is mostly going to cover what we did in Chapter 7 and the very, very beginning of Chapter 8. So you'll notice that many of these first few questions are Chapter 7 related, and then it'll move into a little bit of Chapter 8. Things to remember in terms of Chapter 7 is that in order to use anything having to do with a normal distribution, you need to check whether or not you have a normal situation. And so if we're talking about looking for proportions, remember we can check the large counts condition. If we're talking about means, then we know that we need to look at whether or not the population it comes from is normal, and if not, try to use the central limit theorem, where so long as the sample size is greater than 30, then we can approximate our normality. Okay, so number 4 here at the top says the time it takes students to complete a statistics quiz has a mean of 20.5 minutes and a standard deviation of 15.4 minutes. What's the probability that a random sample of 40 students will have a mean completion time greater than 25 minutes? So I'm trying to find the probability that the average completion time is greater than 25 minutes. And so in order to do that, I need to use information related to the sampling distribution. And so in this case, because the sample size is 40 students, which is more than 30, the central limit theorem says that I can go ahead and use my normal distribution. Now also need to remember that the standard deviation I'm going to use is the standard deviation I was given over the square root of n. So that would be a standard deviation of 2.43. And so then I can use my calculator and do a normal CDF, plugging in my lower bound, which is the 25, my upper bound, which is a really large number. The mean stays the same at 20.5 with a standard deviation of 2.43. And I press OK, and it gives me 0.0322. So right in here. Okay. The next question, similar idea. Incomes of a certain large population of college teachers, a normal distribution. So that's good to know from the beginning. Normal distribution with a mean of 60,000, standard deviation of 5,000. 4 teachers are selected at random to serve on a salary review committee. What's the probability that the average salary exceeds 65,000? Okay, so because they told us the population is normal, we don't need central limit theorem. For our standard deviation, again, we're going to take the standard deviation we were given and divide by the square root of the sample size. So that's 5,000 divided by the square root of 4, or 2,500. And then again, plug into your normal CDF in your calculator, with 65,000 being the lower bound, some really large number as the upper, 60,000 as the mean, and 2,500 as the standard deviation. And I get a, okay, a random sample of size 25 is to be taken from a population that's normally distributed, mean of 60, standard deviation of 10. The mean of the observations in our sample is to be computed. The sampling distribution. So sampling distribution should be approximately normal and should have a standard deviation that follows from the population standard deviation over the square root of n. So this would be 10 over 5, which is 2. So it should be approximately normal with a mean of 60 and a standard deviation of 2. The next question, the scores of individual students on a college entrance exam have a left skewed distribution with a mean of 18.6, standard deviation of 6. At Millard North High School, 36 seniors take the test. The sampling distribution of mean scores for a random sample of 36 students is approximately normal This is following from the central limit theorem, where n is greater than or equal to 30. Okay? 10 says, the distribution of prices for home sales in Minnesota is skewed to the right with a mean of 290,000, a standard deviation of 145. Suppose you take a simple random sample of 100 home sales from this very large population. What's the probability the mean is above? The mean is above 325,000. Okay, we have a standard deviation of 145,000 over the square root of 100. So that's 14,500. Back to my calculator. Normal CDF. I'm plugging in the 325,000, a very large number for the upper bound. My average is 290,000 with a standard deviation of 14,500. And that gives me 0.007894, so we're gonna go with C on this one. All right, so these two here, these two multiple choice are stemming from chapter 8. The first one is basically asking us to interpret the confidence interval. Remember that interpreting the interval is when we're saying we're this percent confident that this range gets the actual value. And so we're gonna go with C on this one, since that's the one that gives us the 90% confident that the interval is capturing what we're really looking for. The second question says you're collecting a random sample of size n from a population and computing a 90% confidence interval. Which of these is going to give us a wider interval? So decreasing confidence and increasing sample size actually make our intervals more narrow. And increasing the confidence level should make the interval wider in order to capture as much as possible. Okay? Now, this question here is directly from, I believe it was your quiz. And so let's take a look at it. According to the 2000 U.S. Census, 80% of Americans over the age of 25 have earned a high school diploma. We take a random sample of 120 and record the proportion p hat of individuals that have a high school diploma. So we want to know what are the mean of this sampling distribution and the standard deviation of the sampling distribution. And so the mean, recall, should just be p, in this case 80%. The standard deviation should be p times 1 minus p over n square rooted, so that would be 0.80 times 0.20 over 120 square rooted. So let's see, 0.8 times 0.2 over 120 gives me 0.0365. Now in order to use this, I need to check the 10% condition. So is it reasonable that the number of Americans 25 and older is more than 1,200? So yes, this seems reasonable. So we're good with these calculations, okay? The next question says, what's the approximate shape of the sampling distribution? Since we're talking about proportions, we're gonna check that large counts condition. Remember that large counts is when we check n times p, greater than or equal to 10, and n times 1 minus p greater than or equal to 10. So in this case, n is 120, p is 0.8. So that's 120 and 0.2. So 120 times 0.8 is 96, greater than or equal to 10, so that's good. And 24, also greater than or equal to 10, so that's good. So the shape is approximately normal. Okay, and the justification is checking that large counts condition. And then finally, C says, suppose the sample size was 30 instead of 120. Compare the shape, center, and spread of this sampling distribution of parts A and B. So if n is equal to 120, we know that the center was at 0.8. We know that the standard deviation was at 0.0365, and that it was approximately normal. If I change n to 30, the mean stays the same. The standard deviation should increase, right? Because now we're going to divide by 30 instead of 120. And now it is not normal anymore because 30 times 0.8 and 30 times 0.2 will no longer meet the condition. So this is 24 and 6, which 6 is not greater than or equal to 10. Okay? All right, this question stems from 7.3. And so we have information at the top. It says the length of these advertisements is normally distributed, mean of 28, standard deviation of 5. Each hour during programming, 45 minutes are devoted to the program and 15 are set aside for ads. To fill the 15 minutes, the producer randomly selects 30 advertisements. Okay, so that's 15 minutes, 30 advertisements. Describe the sampling distribution of the sample mean length for random samples of 30 ads. So the sampling distribution should have a mean, x bar, which is equal to the mean of the population, which is 28 seconds. My standard deviation should be equal to the standard deviation over the square root of n. So that's 5 over the square root of 30. So 5 divided by square root of 30 is 0.913 seconds. And this, of course, is dependent upon the population of ads being greater than 300, which seems reasonable. And the shape of this distribution should be approximately normal because the population is normal, okay? If 30 advertisements were randomly selected, what's the probability the total time needed to air them will exceed 15 minutes available? So we're talking in terms of seconds. So 15 minutes times 60 seconds is 900. We want to find the probability that the average time would exceed 900. So you know what, instead of looking at all of them combined, let's find an average. That's what we really need. So if we're referring to 15 minutes that are available, 15 minutes times 60 seconds divided by the 30 ads that we have should be 900 divided by 30, which is 30. So we want to know the probability that the average ad is more than 30 seconds. Okay, and so we know that we have a distribution that's normal or approximately normal with a mean of 28 and a standard deviation of 0.913. And so then I'm going to go ahead and use my normal CDF. And my lower bound is 30. My upper bound, I'm going to make a large number with a mean of 28 and a standard deviation of 0.913. And so I do that and I get 0.0142. And so this is the probability that the total time will exceed 15 minutes. All right, and here's the last example related to 8.1. So crop researchers are interested in the productivity of a new variety of corn. They plant 25 plots with randomly selected seeds of the new variety, record the yield in bushels per acre, and find that a 99% confidence interval from 118, to 130. Right, 99% confidence with the 25 plots. A says, what's the point estimate from this sample? So essentially, I just need to find the value that's halfway between these two. So 118 plus 130 divided 2 is 124. So if my point estimate is 124, then my margin of error is the difference between 130 and 124, which is 6. Okay? It says interpret the 99% confidence interval. Remember that interpreting is when we say we are 99% confident. The interval from 118 to 130 captures the actual mean yield in bushels per acre. Okay, and then lastly, interpreting the confidence level. That's when we talk about what exactly this means. So if this method were repeated many times with samples of the same size, (99% of the resulting confidence intervals would capture the actual mean yield. All right.